This is Unit 1, Day 6 notes. They start on page 14 of your note packet. And a few things just to remind you of. In the previous class, we did our continuity foldable, and solutions to that are in BB9. If you need to check your answers, or you're just not sure if your version of your answers are correct, you can compare them. If you didn't get a chance to talk to somebody or myself in class. Also, just a reminder, if I haven't said this already in class, I should have at least by now a couple of times. A score of 75 or a score of 100% is proficient in Con. But 75 will get you a B in the grade book, 100% will get you an A in the grade book. You can always go back at any time during the year and improve your score to 100%. Just let me know, and I'll go back and adjust those Con grades. Okay, so we are on day 2 of continuity. So by now you should have a really good functional idea of what continuity is. Okay, so what is continuity? When do we have it? When do we not? So continuity is being able to draw something without lifting your pencil, right? Continuous means that we are not, we don't have any holes or jumps or asymptotes or oscillations that tend to have gaps. And those are rare. The oscillations are rare. So continuity is when our limits and our function values all end up being the same. They all converge. When do we have it? When we don't have any discontinuities. I know it sounds a bit redundant, but we talked about the types of discontinuities. And when do we not have it? When we don't have it, we start to see those discontinuities. And then we talked about, some discontinuities are removable. Like a hole is removable. It's the only removable discontinuity. A jump or an asymptote are not removable. Those are essential. They have to stay there. And so that's kind of this today's notes is kind of getting at that. When do we have continuity? When do we not? Okay, and it really focuses on piecewise functions. So obviously what's happening is, we've got different functions in different domains, and everything's switching. In this case, everything is switching at -1. Okay, so we need to know what's happening at -1 right here, right? This is when x is equal to -1. We want to know what's going on right here. Okay, and so with all of these things coming together and transitioning at that location, we want to make sure, if we want to be continuous, we want to make sure that we all come together there. So let's take a look at then, let's take a look at x values less than -1. So let's take a look at this part of the graph. I think that's what I do first. Okay, so I am just going to plug and chug. So if I put in -5, 5 plus -5 is 0. I'm just going dot for dot. I have a finite domain here. I'm just graphing it dot for dot. Let's put in -4. 5 plus a -4 is 1. Let's put in -3. 5 plus -3 is 2. Let's put in -2. 5 plus -2 is 3. I'm even going to put in -1. 5 plus -1 is 4. Okay, now notice what I did there. Because this is strictly less than -1, I don't have a function value there, right? But I know that as I approach -1, I'm approaching 4. So I put an open dot there. Okay, so that's that part of the domain. Now let's look at, I'm just trying to get there we go. Let's try this here. So I get my clicks right. Okay, let's take a look at what's happening here. Obviously I don't have some coding correctly here. Let me see if I can change that on the fly here. So I told you that it's rare that I actually make it through all this in one shot without a mistake. Let's see here, what's going on here. We got 7 and 7 and 7. Okay, I gotta pause here, figure out what's going on. Okay, we're back now. So we got that. We talked about why that's an open circle. So let's go to the next expression in the piecewise function, and that is when x is equal to -1, the y value is 3. So that's why we have that filled in dot there. Right? That's physically a y value. Okay, and that's all we do at -1. And then the next entry is when x is greater than -1. So notice again the open dot, because I want to know what's going on with this function at -1, knowing that we never really reach -1. That's not part of this function's domain. But if we put in -1, then we have -4 times a -1/2. It's a +2. Okay, and then I'm going to keep going. I'm going to put in 0. And when I guess I don't put in 0. Oh, that makes a lot of sense though. I don't put in 0 because of this half here. So I skip over to 1 and put in 1. This is kind of just being efficient, right? 1 minus 3 is -2 times -1/2 is +1. And then I skip over to 3. 3 minus 3 is 0 times -1/2 is 0. And then I skip over to 5. 5 minus 3 is 2 times -1/2 is -1. And so that is that function. So if we look at what's happening with -1, we have a jump. And we know a jump is an essential discontinuity. So we have a limit that doesn't exist. So we know we know that that limit can't exist there. It's not removable. And so again, it's a jump discontinuity. That's what it looks like. Okay, let's take a look at this. We have the limit as x approaches -1 from the left of 5 plus x. So notice that I have to back up here, but it's this top function here, right? It's and just bear with me as I get through this. There we go. It's this top function. So I'm doing this algebraically. Okay, so this is the algebraic solution. If we didn't graph this and we wanted to determine if this discontinuity is removable, just algebraically, without graphs, then we have to grab this first function and take its limit as we approach -1 from the smaller values. That's why we have it minus sign up here. And we can do direct substitution here. We can put -1 into the expression, come up with 4. So we know the limit is 4. That's that open circle that we had on the graph, right? Okay, then we know the function at -1 is 3. That's the function value. That's just function value. Nothing, no calculus there. And then we take the limit as we approach -1 from the bigger values, which is this one. So again, with direct substitution, we're going to put -1 in there, and we're going to get 2, right? That's the graph. That's describing this and this and this on the graph. This is a limit because it's an open circle. This is a function value, so it's a closed circle. This is a limit, again, because of the open circle. So we got the limit and the function value. And we know by the definition of continuity, if those numbers are all the same, then we have a continuity at that location. These numbers are not all the same. As long as there's at least one that's different, we have a discontinuity. So we know that we have a discontinuity. Because none of them are the same, we know we have some jumping around occurring here. So we know we have a non-removable discontinuity. The limits aren't the same. Okay, so that's where we get our jump from, is because the limits are not the same. So this is going back to the definition of continuity, right? The limit has to equal the function value. These limits don't equal the function value. Therefore, not continuous. Okay, another variation of the piecewise function is to find values for which this would be continuous. So in other words, let's go back here. We have a jump discontinuity on this problem that we can't fix, but we want all of these values to come together as one. We want to squish all that together, okay? That's what we want to accomplish with specific values for C and D. So we have just to kind of preface what we have here, we have a parabola here. We've got a line here, right? And this is a constant value right here, or a dot, however you want to look at that. So we want to find the value of the constants that make the function continuous at x equals 2. So we want all of those values to be equal, all of those function values to be equal. So let's just start setting them equal to each other and see what we get. So let's start with the top two values. We're going to set the parabola equal to the dot, or the function value. And we know that we are focusing on x equal to 2, so we're going to put 2's in here for x's. And if you notice when we do that, when we put those 2's in, we can find the value, the c value. So we put 2 in. Oh, and I'm going to do this for the last 2 as well. Okay, so we're going to go ahead and put 2 in, and we've got 2 squared minus 4 times 2, so it's 4 minus 8, that's negative 4. Okay, and then we're going to put 2 in for here. So we got c equals d plus 2. That we can't do anything with. So we might as well solve this for c first and then come over here. So we know c is negative 4. Then we can put negative 4 here. And we can solve for d, bring the 2 over to the other side, and know d is negative 6. So if c is negative 4 and d is negative 6, all of these will have the same value as we approach 2. So let's look at this graphically speaking. If we look at this, then this function value, when x is equal to 2, y is equal to negative 4, it means you got to be down here. There's that dot, so to speak. And so if that's the case, then and you graph this, that parabola is coming through at that point there, going right through that point. Kind of looks like maybe it's the vertex of that parabola. And then when this is negative 6, then this is the line that results, right? If we extend this, it would go and have an intercept of negative 6, intercept of 1. So notice that all three of these piecewise functions come together at this location. So the function is now continuous. We can go right from the red parabola through the blue dot to the blue line without lifting our pencil. So those are the values that make that piecewise function continuous. And when we get into class, we'll do takeaways and look at those topic questions for continuity.